Welcome to Solved Papers channel. My name is Mr. Godfrey. This is Cambridge IGCSE Physics. We are dealing with topical questions. Topic in this video is going to be sound. October-November 2019 exam Cambridge series. You can get these and more topical questions, of course, from this site. Softpapers.co.uk. I'm an experienced Cambridge International curricular teacher, and I know what I'm talking about when I say topical questions is the way to go. Topical questions exposes you to the content of a given topic from many different angles, and you will be sure once you do topical questions for several years, 2019, November 2019, June, 2018 and so forth, out to 2016 on a given topic. Of course, read the notes first before you attempt the questions. Read your notes, read your textbook on the same that particular topic, and then come attempt the questions. You will be surprised how easy physics is when you do topic wise. In every topic, I'm giving you this kind of writing. This kind of writing tells you from where the question was set from. This is, of course, the first is the code for physics. Of course, for chemistry is 0620. For physics is 0625. 31 is the variant. Of course, these are structured questions. Variant 3 and variant 4. And ON is October, November. This is 2019. And this is the number of questions on this paper 3, 1, from where it was set. So these are the things that I needed you to know. And before we start, if you have not already subscribed to my channel, please click the subscribe button and hit the bell icon below. This way you will be notified every time I upload a new video. I wish we get started. Question number 1. Fig 8.1, this figure shows a student listening to the sound produced by a tuning fork. State part 1, state how the tuning fork produces sound. Of course, just like any other sound producing object, the tuning fork vibrates. So produces sound by vibrating. You knock the tuning fork on a desk, then you listen to its vibration. You'll hear sound. So it's by vibrating. Part 2. Complete the following sentences. Choose a word from the box. We have electromagnetic, longitudinal, and transverse. And we are told that a sound wave is, of course, sound wave is longitudinal. What does longitudinal mean? Longitudinal means the vibrations of the particles parallel to the direction of the propagation of sound, right? So that is what longitudinal means. Of course, transverse means the vibration of the particles either in air or in water, wherever the sound is traveling through, perpendicular at an angle of 90 to the direction of the travel of sound. That is what longitudinal and transverse means. Part 3, a loudspeaker produces a sound with a frequency of 25 kilohertz. A student with a healthy ears cannot hear this sound. Explain why. Student with a healthy ear cannot hear this sound. Of course, the frequency of 25 kilohertz is well above the upper limit of human hearing range. The human hearing range is 20,000 hertz. So the human hearing range, you can state that the human hearing range is 20 hertz to 20,000 hertz. So a frequency of 25 kilohertz is above this, is above the hearing range. It's above the hearing range of humans. That's why, though the student has got very healthy ears, he cannot hear this frequency of this sound. Okay. B, part B, Fig 8.2, this figure represents a sound wave traveling in air. It's drawn to full scale. The air particles are moving. On Fig 8.2, draw two arrows in opposite direction to show the movement of the air particles. Two arrows. So I'll draw one arrow in this direction, then draw another arrow in opposite direction. Remember, I said that longitudinal, the vibration of the air particles is parallel to the direction of the propagation of sound. So that's how you get this one mark, by drawing those two arrows. Use Fig 8.2 to determine the wavelength of the sound wave. All right. Since this is drawn to scale, okay, it's full size, I'll require you to be able to measure the length from here to the last one. Use your ruler and measure that length. And of course, when you do that, you'll find that the length is 14.4 centimeters. This length. The length here is 14.4 centimeters. Use your ruler and measure that. Of course, you need a hard copy of this question to be able to do that. And then determine how many wavelengths do we have in this Fig 8.2. So our wavelength is, for example, from here. Of course, you draw the corresponding point here to here. This is equivalent to our wavelength. Okay, that distance there is equivalent to a wavelength. So how many wavelengths can you see here? I can see from here to here, that's one wavelength. From here to here, two wavelengths. From here to here, three wavelengths. And then from here to here, four wavelengths. So 14.4 centimeters. This is representing four wavelengths. Of course, I hope you know lambda is the symbol for wavelength. And therefore, what is one wavelength? What is lambda? Okay, to get lambda, you cross multiply. All right. So the lambda here is going to be lambda is equals to be how many centimeters? So I can say lambda is equals to 14.4 over 4. Of course, this centimeters. And when you divide 14.4 over 4, then you'll find that lambda is equals to 3.6 centimeters. And that is the wavelength. We are taught to use this Fig 2 to determine the wavelength. There's nothing else given in this other than you're being told this is drawn to scale. When you're told full size, you're told it's drawn to scale. So you use your ruler to measure that distance. Very good. C. Let's go to C. describe a method of using water waves to demonstrate refraction. What is refraction? Refraction is the bending of light as it moves from one medium to the next. So at an angle, of course. So of course, if I can have this, then I tell you this is shallow and this is deep. This is shallow waters and this is deep water. And then we have this coming. Let me not bend it too much. Then of course can use this. This is the direction of the waves. The direction of the waves at that boundary. So when they get to this boundary, these waves will bend this direction. The waves will bend in this direction. And as you can notice, the wavelength has increased. So the wavelength is this distance here. That distance is wavelength. When you consider the same distance here, you can see in the deep the wavelength has increased. All right. So describe a method of using water waves to demonstrate refraction. These are 4 marks, so you need to supply enough points. I say that use dashes or hyphens to start to show an examiner where your point is starting from. So basically you can do well to remember the demonstration that we do in class using the water, using the question number 2. And as we proceed with question number 2, it's great you're watching this video. Remember that practice will help you. Practicing on these questions will help you to remember or to learn better. So I encourage you to go to this site, softpapers.co.uk. You will get the same paper that I'm solving right now. And this is the site I'm talking about, Soft Papers. Soft Papers is this site here. Of course, I'm sure you're familiar with this site by now. It's a very resourceful site with Cambridge for past papers. So you go to 2019. You can get other years. All these years I've got topical past papers as well. Go to 2019. This is what we are working with. 2019. Of course, you'll find Physics IGCSE 2019 topicals. For November, you'll have multiple and structured questions. Of course, solved. You're given an example of the solved there. Of course, you can also get 2019 June, both structured and multiple choice. The one we are dealing with right now, which is sound, is this one here. But I need you to click here to get all topicals in a Zof folder. So when you click here, then this will open, and this is where you'll get the papers from. Of course, there are the papers that are premium. You'll get papers for 2019, 2018, 2017, and 2016. Of course, for both physics and chemistry, if you're doing chemistry, papers are reasonably price of £9 for structured and for multiple choice as well, for November and June for all the years that are indicated here. So you may request your parents to assist you in acquiring these papers. Buy as many as you can, practice as many topical questions as you can, and that will be a worthwhile investment. You'll find that you are well equipped and prepared to face the exam confidently. 2021 June, when you'll be doing your IGCSE physics exam. That out of the way, let's continue with question number 2. A boat race starts on the sea but close to the land. Fig 9.1, this one here, shows the boats at the start of the race. On the land, a cannon produces a loud bang to start the race. There is a flash of light at the same time as the bang. Here, so here we have a cannon producing sound and light. At the start of the race, the sailors watch for the flash of light from the cannon. Suggest why the sailors watch for the light rather than listen the bang. What do you think is the reason? Of course, the reason is obvious. Light is faster than sound, so the light will get to them before the sound comes. So light travels faster than sound. Faster than sound. So they will see the light first before they hear the sound. They'll see light before they hear the sound. So if you're waiting for the sound, you'll find that you are some seconds later or late than those other guys who have seen the light. Okay. So part 2. One of the sailor is 500 meters from the cannon. She measures the time difference of 1.6 between seeing the flash and hearing the sound. Calculate the speed of sound. Right? We know that speed is equals to distance over time. And of course, the distance here is 500 meters, and the time it took for the sound to travel from the cannon to her was 1.6 seconds. So the speed will be around 312.5 meters per second. This is basically around 313 meters per second. The units given. You don't need to write the units again. Part 3. The value of the speed of sound obtained in part 2 is lower than the expected. Of course, the speed of sound is around 330. So what could be the reason for this difference? The reason here is due to the experimenter's reaction time. So the reaction time, time of the sailor. The reaction time of the sailor to start and to stop the watch. You must notice that the time is 1.6 seconds. That is basically like starting and stopping almost the same time. So the reaction time is going to bring an error, and that's why the sound here, the speed of the sound is lower. Okay, if the reaction time is precise, then the speed of sound should be around 330 meters per second, or thereabout. Okay. Part B. The race is held close to a part of the coast with high cliffs. A sailor hears a second bang shortly after the first bang. State the term for the second bang and explain how it's produced. Of course, the second bang is what we call echo. What is echo? Reflection of sound off a surface. So it means that sound was reflected off the cliff. Reflected off the cliff. That's why the echo was heard. Number 3. Fig 4.1. Of course, this is question from variant 4.1, question number 4. Fig 4.1 shows a loudspeaker that is producing a sound wave in air of frequency 15,000 Hertz. Right? So this is a loudspeaker. Of course, the hollow paper cone connected to power here. I can draw this to show that it's connected to AC. Describe how the cone of the loudspeaker produces this sound. How does the cone produce this sound? We are supposed to describe, and how much you write is dictated by the number of marks. You cannot just write one sentence and expect to earn these 3 marks. So write 3 or more points to be able to earn these marks. So to produce the sound, the cone of the loudspeaker vibrates. The cone vibrates forward and backward. Forward and backward. Don't forget, sound is longitudinal. Backwards causing the neighboring air molecules. The neighboring air molecules to vibrate. To vibrate. Okay. What this does, it causes regions. It causes regions of compression and rarefaction. It causes regions of compression where the air molecules are close together, and when it moves, of course, compression is when it moves forward, and when the cone vibrates backwards, then it causes regions of rarefaction. Rarefaction. And this is what transfers sound and transfers sound energy to the air molecules. So what it means by 15,000 Hertz, this means that the vibrations of the cone, is the vibration of the cone is 15,000 times every second. So there you are. You have described how the cone of the loudspeaker produces this sound of 15,000 Hertz. So it vibrates 15,000 times each second. You can see I provided 3 points. Point number 1, 2, and 3. Of course, an examiner seeing, of course, I'm an examiner myself. An examiner seeing this kind of writing from a student is pleased, knows the student is knows what they're doing, and you'll be encouraged to give them marks and be lenient with them, even if the points are not correct entirely. Of course, you don't award wrong points. B, the speed of sound in air is 330 meters per second. Calculate the wavelength of this sound. Of course, we know that we are told the frequency is 15,000 Hertz. We know that speed, which is frequency times wavelength. We are supposed to find the wavelength. So make wavelength subject. Wavelength is speed over frequency, and the speed we are told is 330 meters per second. Our frequency is 15,000 hertz, and therefore when you use your calculator and divide this, you'll get a wavelength of 0.022 meters. So you can see there are no units given here, so you must apply the units, otherwise you'll be penalized one of these 2 marks, meters, right there. So 0.022 meters. Okay. Part C. Part C. Part C. Before we get to part C, let me welcome you to my online classes. I will ask you to please join me in my own classes. I do tuition online. Of course, you can visit this site and register, spacademy.co.uk. The site I'm referring to is this one here. SP Academy means Salt Papers Academy. We are a group of teachers who solve these CI papers. So we are experienced, we know what you're doing. We can help you get your A-star if that's what you're looking for. Of course, I need you to come to this student guide. If you are a student, if you are a tutor, you can look at tutor guide. Of course, click here for a step-by-step guide for students dashboard. When you register, you get create your own account. You will be provided with a dashboard where there are plenty of functionalities from where you can book a lesson from any tutor of choice. Also, watch this video. I encourage you to watch this video to get familiar with our online classes. Of course, this side is currently we are offering ICT, mathematics, physics, biology, and chemistry. We are adding more subjects as demand comes through. Of course, you can have time and go through the site. So what I need you to do is to come to the login here. Of course, you register. If you are a student, you choose student. If you are a tutor, you choose that. Provide a correct email, because when you register, you get an email with which you're going to be able to activate your account. Then now you can sign in. You can sign in and book a lesson. You can find a tutor, or explore our site, and I'm sure you will like our site. So welcome to my online classes. I will help you, and I guarantee that you will get a great opportunity of getting an outstanding grades of choice. Part C. The loudspeaker is placed at a considerable distance to the left of the barrier. You can see the barrier here, right here, with a gap. The width of the gap is double the wavelength of the sound. Sound from the loudspeaker reaches barrier and passes through the gap. Okay, of course, this is about diffraction. Okay, pass through the gap. You are told that on Fig 4.3, this one here, which is not drawn to scale, sketch a diagram that represents the sound wave as a series of wavefronts traveling towards the barrier in the gap and traveling away from the barrier. Okay, so here we are. So the sound waves, the barrier, the gap of the barrier is double the wavelength. So you can see how big the barrier is. So I draw one wavelength there, one wavefront there. I draw another wavefront there, assuming that that wavelength is half the gap. This is wavelength. this distance here. So since the wavelength is of the sound wave is less than the gap, the wave, once it goes through the gap, will only bend at the edges. Something like this. It will only bend. The wavelength will remain the same. It will only bend at the edges. Something like that. So that's what I expect you to draw to earn these 3 marks. Okay. Question number 4. Question number 4 is appeared on variant 4.2, October-November 2019, and this was question number 5 in that paper. You can, of course, refer there. Question number 4. One difference between longitudinal and transverse wave is that longitudinal wave consists of compression and rarefaction. That is one difference. All right. Explain these terms using ideas of particles. So what is compression? Compression is when the particles through which the sound is traveling are close together. So at compression, the particles of the medium, of course, through which the sound is passing through, of the medium, are close together, or they are compressed. Rarefaction, here the particles, because we are supposed to explain this in terms of particles, the particles of the medium, of course, through where the sound is passing through, are apart, or are at a distance, from each other. Part 2. Describe one other way in which longitudinal waves motion differ from transverse wave motion. We are describing motion, the difference in motions. The longitudinal wave motion, vibrations of the particles, are parallel to the direction of the wave motion. To the direction of the wave motion. What about transverse? The vibrations are perpendicular at an angle of 90, are perpendicular to the direction of the wave motion. Very well. B. A sound wave of frequency 0.120 kilohertz traveling through a rock at a speed of 3,500 meters per second travels through a rock at a speed of this. Calculate the wavelength of the wave. Of course, you know that the speed of a sound is greater in solids than both in liquid and air. Right, so we know that velocity or speed of a wave is frequency times wavelength. We are supposed to calculate wavelength, which is speed over frequency. We are given speed here as 35 meters per second for that 500, and the frequency is 0.1 2 kilohertz. This is equivalent to 100 hertz, 120 hertz. Of course, kilo is 1000, and therefore 0.120 times 1000, this gives you 120 hertz. So you have to change that into hertz. Therefore 3500 divided by 120, you get 29 meters. So the wavelength is 29 meters. You can see there's no unit here, so you must give the unit right there. Part 2. The wave travels from the rock into air. State and explain. 2 answers they are required for you to earn these 2 marks. State and explain whether the wave will be audible to a healthy human ear. Right? Will it be audible? And of course, the frequency does not change. The frequency from one medium to the other does not change. So frequency remains the same. Same. So same is 120 hertz. And we know that a human ear can hear frequency between 20 hertz to 20,000 hertz. So 120 is in between here. So the stating whether it will be audible, yes, it will be audible. Will be audible. Okay. Explanation of course is what we have indicated. Frequency does not change. Does not change as it moves from one medium. As it moves from one medium to another, from one medium, that is from the rock to the air, the frequency remains the same. So it will be, so frequency will still be 120 hertz, which is audible. Okay. Question number 5. Question number 5. This question is from variant 4.3. Question number 6 it is. Fig 6.1 represents wavefronts of a sound traveling in air from left to right. From left to right. State the name given to the region around A in the diagram. This region is compression. Region B is rarefaction. On Fig 6.1, draw a double-headed arrow to show one wavelength. You can draw this one wherever you choose. I will choose this point here, and the corresponding point is this one here. So that distance is equivalent to one wavelength. You can also, if you choose this point, then the corresponding point is this one here. So this is also an equivalent of one wavelength. You can have as many points as you desire, but you're only taught to choose to draw one. Okay, so let me remove this. So that is what I draw, and I'll get that 1 mark right there. Okay. Part C, loudness of a sound increases at the same pitch pitch remains same, but loudness has increased. State and explain any changes that would be in the pattern of wavefronts shown in Fig 6.2. So loudness is due to increase in amplitude, right? And of course, in this case, the wavefronts will be much closer at compression and farther apart at their rarefaction, so that there is an increase in wavelength. Wavelength basically means an increase in amplitude, right? In this case, so state. So let's state what will be the change in the pattern of the wavefronts there. So the wavefronts will be closer at compression at compressions and farther apart at the rarefactions. Of course, that will be what will be observed, the change in the patterns. Of course, the explanation is loudness. Explanation is loudness only affects the amplitude. But the wavelength remains the same. I think they say there will be an increase in wavelength. That's not the case. It remains the same. It remains the same because as the compressions decrease, the rarefaction are increasing by the same margin. The rarefactions, the compressions are decreased. Therefore, the wavelength will still be the same. Then lastly, D, state also and explain. We are told two waves passes into water. State and explain, oh sorry, not two. The wave passes into water. State and explain any change in the patterns of wavefronts shown up there. So it has passed into the water. Initially it was moving through air. So it has moved from one medium which is air into water, which is another medium. Therefore, at water, in water, the sound, of course, travels faster. Sound is fastest in solids. It is faster in liquid than in air. So in water, the sound travels now faster. Sound travels faster in water than in air. That one we know. So you must earn these 3 points by supplying enough points. So the speed increases. In water, or the speed increase in water means the wavelength now will increase. The wavelength will increase. Let me write it here. Means the wavelength will increase. Remember, speed is equals to frequency times wavelength. and the frequency remains the same in refraction. So wavefronts, wavefronts will be more spread out, Okay, this could be the statement. State any change in the patterns. So the patterns were in the pattern, the wavefronts will be more spread out. And then now the explanation is that the sound travels faster in water than in air. So the speed increase in water means the wavelength will increase, and of course that will mean more spaced out wavefronts. Very good. That's the last question. Thank you for keeping here till this question. I hope this is helpful to you. See you in my next video. Cheers and bye.